Hello, it's Dr. Della Corte back with Physics 313R, Lecture 3 on linear algebra in our Introduction to Quantum Computing course. So, just as a reminder, the content of this course comes from the book Quantum Computing for Everyone by Chris Bernard. You can find it on Amazon or elsewhere. I highly recommend everyone to getting this book so that they can work independently next to the lecture slides through all the problems in the book and keep their study journal up to date. Great. So first off, we're going to make a few simplifications in this class. In the general theory of quantum mechanics, one works with infinite dimensional vector spaces, which is something that we don't need because the spins and polarizations that we use to define qubits with, they don't need that at all. We can simplify the problems quite a bit. So the math that we are going to use is pretty much standard additions, multiplications, some square roots, and a bit of trigonometry. Now, the way we use these standard math operations is going to be in a new format that most of you won't be familiar with. And so today's lecture is really a means of introducing you to all of the mathematical concepts that we need in this class. So it's a subset of the field of linear algebra. Um, but we will also review the math as we need it as we continue going through the book. I think this is about the time where someone that just buys the book will either put it in a shelf and not do it anymore, or will really deeply engage with the material. And since that's going to be some step function and energy barrier, I hope that doing this together through the video lectures and in-class discussions, we will be able to take that step with grace and overcome what looks maybe as a formal challenge. The actual math at the end won't be that hard to do, but the formalism behind it can be honestly quite intimidating to people that have not had a big exposure to math before. Okay, with that being said, let's see where our journey is supposed to end. At the end of this class, you should be able to perform the following three things. Well, first, you should understand these three things, and then you should be able to do them. So, the first statement here is that we are going to have an n-dimensional, so a large, what's called set. A set means a bag full of things, and in that bag of things will be these weird things that you probably have never seen before in your life. Those are column vectors that are called cats. We're going to introduce them later. But you have a bag of these cats, and the question is, do all of these cats form something that we call an orthonormal basis? Again, you don't know what that means yet, but at the end of this class, you should be able to understand, oh, this is a set. These are cats, and these cats could potentially form an orthonormal basis, and you will have the mathematical tool to do that. Okay, then let's assume that you happen to have this bag full of cats, and they are an orthonormal basis. Now, can you use them to build another vector, another column vector, cat? This V between this line and the weird bracket here. Can you construct that vector out of these things in your bag? That's effectively the second question. And if you can, how do you do it? Okay, then the third one is, now we assume that you not only have this bag full of vectors that form an orthonormal basis, and this new vector V that is somehow being built out of the individual pieces, the individual column vectors inside of the bag. Once you have both of them, so the bag and the combination of elements in the set, can you find the length of that resulting vector? And you will see that that is actually the easiest part. It's kind of hard to get to the point, but the math for the last part is the easiest one. Okay, cool. If you already did the reading for the class, then you're probably just like, oh yeah, I know all of this. So let me challenge you and ask you, if you look at this here, is this slide crystal clear to you? Do you know what it means when you have arrows pointing up between weird brackets with a bar in between them? And then they're supposed to be equal to something. Or does that look like, cave engravings that someone did 10,000 years ago? It needs to be crystal clear, but let's give it however long this lecture takes to get there. Okay, So here's another important simplification we're going to do in this course. When we introduced the concept of a qubit before, we said a qubit is more than just a switch with zero and ones. It is sort of this sphere where you can have a vector point in any type of direction. It always has the length one, but it's sort of like this radius that sits maybe in the center of Earth and points to all the cities on Earth's surface. So it maps out the entire surface of a sphere. While that is a general representation of a qubit, the math to do algebraically something with it requires you to use what is called imaginary or complex numbers. A complex number is a number that consists of a real part and an imaginary part. Now, it's not incredibly difficult to work with complex numbers, but it does add the level of difficulty. And luckily, for the type of qubits that we're going to use and the algorithms that we look in detail at, we will be able to get away with just focusing on the real part of complex numbers. And the real part of this qubit can be imagined as just the surface or the circumference of a cut that you make through the cube, through the sphere. So if you cut through the sphere, you're going to get what might look like the face of a clock. We already introduced the quantum clock before. And this two-dimensional representation can be built just using the real numbers. And real numbers are the numbers that you typically deal with. They're the things that most people get introduced to only in the high school journey. Okay, so that's what we're going to do. We're going to focus just on this two-dimensional world that can be completely described with real numbers, because we are dealing with two-dimensional spins mainly in this class, and so for that, this is sufficient. In the real world, of course, you would need the three-dimensional qubits. If you want to know about how to do math with it, there are other books that you can use. The one we're using in this class doesn't need it. So there might be a different free credit version of this course in the future. And if you want to go down that road after this course, you definitely have a very solid foundation to build on top of it. Some of the concepts that we're going to cover translate really nicely into the complex description of quantum computing. But again, we want to focus on helping you understand the most important basics, and that we can do with real numbers. All right. So now let's go for the basics of linear algebra. For some of you, some of these slides are super trivial. For some of you, this will already be the moment where you want to quit. I encourage you to stick with it. We'll try to make it as understandable as possible. So what's a vector? In the first approximation, a vector is just a list of numbers. So it's maybe a list. How do you do a list? Well, you put things with a comma in between them in order. You can do that. You can also maybe make a parenthesis, open it up, and then write all the numbers down and close the parentheses. So that might be a way of writing out a list. If you write a list from left to right like that, then you could also say, well, I'm forming a row of numbers. And we are going to call a row of numbers like this a row vector. And the name for a row vector in this class will be bra. Why? Well, there's a guy that invented this formulation, Dirac, and he called row vectors bras, and he called what we'll learn soon column vectors cats, because the way he writes them is with this weird angle bracket here and a line in between. And when you write them next to each other, the ones that come on the left, they are bras, and the ones on the right, they're cats. And if you have one left and one right, you could read them, oh, there's a bra cat. So they form a whole bracket. It's just, physicists trying to be witty, I guess. For us, we just remember numbers listed in a row are called bras. And when you want to quickly write them out, you'd use the angle bracket, then the letter for the A bra vector, and then the line that goes down. And if you want to list them not as a row from left to right, but maybe from top to bottom, like a column in an Excel sheet, you list all the numbers going from top to bottom, then you would say this is a column vector, a cat, and you use the bar, write the letter, and then the angle bracket on the right. How do you remember that the left one is the bra and the right one is the cat? Well, you just remember the word bracket. The one on the left is the bra, the one on the right is the cat. The cat column vector kind of works. The bra, the book has a mnemonic for it. I'm not going to repeat it here, but maybe that one helps you to remember it too. All right, great. If you have vectors, you can draw them. That works really well in 2 and 3 dimensions. Everything else gets really tricky. In 2 dimensions, you can represent a vector like an arrow that starts at an origin and then takes a number of steps in the x direction that is equal to the first number in your list, and then a number of steps in the y direction that's equal to the second number in the list. So why is this a 2-dimensional vector? Because it has 2 numbers. So if you have a list of, say, 5 numbers, that would be a 5-dimensional vectors. If you have only 2 numbers in the list, it's 2-dimensional. The world we live in is 3-dimensional, so 3-dimensional vectors make sense to our brain as well. There you go a certain number of steps in the x, in the y, and in the z direction, and then you find this point here, that's the point x, y, and z, and you connect that point to the origin with a line, with an arrow. Great. So those are representations. We mainly work in 2D in this class. Here's an important rule about vectors that you might remember. When you have a vector, you're allowed to take it and move it around, so-called translating it, as long as you don't rotate it or stretch or compress it. As long as you keep its length the same and its direction the same, you can move it anywhere, and it's still going to be the same vector. And so it's very convenient to take a vector that might start here at 4 and minus 3 and move it to 0, 0. The reason why that's convenient is because the coordinates of the tip of the vector are going to be the first and second number inside of that 2-dimensional list. So here you might have the vector 4 on the x and 2 on the y. So 4, 4, 2 in parentheses. Okay, great. Another thing you can do with vectors is, especially when you write them out like this, starting at the origin, you can see that they the distance from the origin to the tip can be either directly traced, or you can go along the x-axis and then down the y-axis. And if you compare this path to this path, you see, oh, it looks like either a straight line or going along a triangle. And this is actually a special triangle because the x and y axis have a 90-degree angle between them. So this is a right triangle. And in right triangles, we have this wonderful law called the Pythagorean theorem that says we can figure out the length of the hypotenuse by simply multiplying the length of the, by summing up and squaring the lengths of the other 2 sides of the triangle. So you heard probably a squared plus b squared equals c squared. And so we can calculate the length of v. What would it be here? Well, if you have 2 to the square is 4, 4 to the square is 16, 16 plus 4 is 20. So the length of v is the square root of 20, whatever that is, 4 point something. Okay, so vectors of, and then there are some specific type of vectors. They have a length. So when they go down here, they have a length that is exactly 1. So no matter where the vector points, it always has a fixed length of 1. If you have such a vector, 1 you could imagine is that starts from 0 and just goes along the x-axis up to the first ticket to the 1. That would be the vector that does 1 step in the x direction and 0 in the y, so the 1, 0 vector. And that would be a so-called unit vector, in this case, the unit vector in the x direction. You can also have a unit vector in the y direction. You could also have a unit vector in the v direction. For that, you just got to make sure that this doesn't have a length of square root of 20, but it would have a length of 1. So you need to divide the x and y components by a factor that makes it so that you have here a vector that will end there. Great. Yes. So one unit vector is a vector of length 1. Hey, spoiler alarm, qubits will be represented as unit vectors. So important concept. A vector with a length of 1, unit vector. Cool. So if we have, for example, the vector 3 and 1, this is a bracket on the right side, the angle. So it's a cat column. It's a column vector. So we need to figure out the length of the column vector. Let's see if our pen works. So how would that look? Well, if you have a coordinate system, you have 3 steps in the x direction, 1 step in the y direction. So up here would be the tip of your vector. It would go up there. And so you have 3 and 1. So what is the length here? This length L is the same as the length of the vector. So we say the length of a vector always goes between parallel bars, and then we write the vector in there. So this vector also has a bar like that. Okay, what's the length of this vector? L is going to be, this here is the length of 3. This is the length of 1. So we're going to have square root of 3 to the square plus 1 to the square, or 9 plus 1 square root of 10. So that's the length of this vector. Great. You should be very comfortable doing these type of operations. What else can you do? When you have a vector, you can make it longer. You can multiply it by a number. That is so-called scalar multiplication. So if I have the vector A here, and I multiply it by 3, then it means I just stick the same vector 3 times on top of each other, end to tip, end to tip, and then I'm going to get a resulting vector that goes from here to here. So 3 individual A vectors are the same as one really large red vector here. So that's the rule of scalar multiplication. You can just multiply the number and the scalar C by which you stretch it with each of the components of the numbers in your list, with each of the numbers in the vector. Great. What happens if you take our vector 3, 1 that we had before and you scale it by a factor of 1 over square root of 10? If you do that, then you take the vector, take each of the components, each of the numbers in the vector, and divide them by square root of 10. What will that do to the vector? Let's get rid of my pen here. So if we do the same calculation before to figure out the length of this vector, that is now going to be the square root of this guy to the square. So 3 over square root of 10 to the square plus 1 over square root of 10 to the square. And that's going to be 9 divided by 10 plus 1 divided by 10. But 9 tenths plus 1 tenth is 10 tenths, and that's 10 over 10 is 1. Square root of 1 is 1. So the length of this vector here is going to just be 1. This is how we can create unit vectors. If we have a vector, like the vector 3, 1, that has a length of square root of 10, we just divide the whole thing by square root of 10, and thereby we shrink the vector to the size it needs to have, or potentially stretch the vector to the size it needs to have in order to get it to be 1. All right, great. You can do these scalar multiplications also with matrices. So if you have multiple vectors collected in what's called a matrix, and you do scalar multiplication, you just multiply each number in the matrix with that scalar. Okay, great. Yep, so U is now a unit vector. Still points in the direction 3, 1, but only takes a step size of 1. Great. Another thing we can do is we can add and multiply. We can add and multiply bras and cats together. But vice versa, you have to be careful. So if you have, what is this, a bra or cat? It's a column vector, it's a cat. And another column vector. If you want to take them and add them together, you just do it. You just take the first number in the A vector and the first number in the B vector, add them together, and that gets you the first number in the sum of the two vector. And you do the same for all of the different numbers in your back. Great. So in a two-dimensional case, if you have a vector A and a vector B, and you add them together, you assume that you can just imagine that you grab your B vector and you stick it at the end of the A vector, and then it forms a triangle. It's not a right triangle, it just forms a triangle. And the distance from the origin to this tip here is the same, or the coordinates of the tip here is going to be the same as the coordinates you're going to get from doing this A plus B calculation that you see on the slide. Now there are some special vectors, and they are orthogonal. Orthogonal vectors are such that they do form a right triangle. There's a 90-degree angle here between the u and the v vector. So what do you know about u, v, and u plus v? Well, since u and v are right angles, they should form a right triangle. And so u square plus v square is equal to u plus v square. So this is effectively just restating the Pythagorean theorem for vectors, saying that if two vectors are orthogonal on each other, then this equation must hold. Okay, great. Now, when you have a bra and a cat, so a row vector and a column vector, you can actually multiply them with each other. What that is sometimes called in linear algebra is a dot product, and that results in a number. It measures, if you have two vectors, how big the projection of one vector on the other vector is. But we're going to walk through it here. So let's grab a row vector here, the A1, and a column vector B, and multiply them with each other. So what are you going to get out? It's supposed to be a number. So let's grab the pen. Here, our A vector has these n components, and our B vector has n components. And now we're supposed to calculate somehow the product between the two. And how do you do it? Well, you have probably learned in high school at some point when you do smaller matrices and smaller, maybe 3-dimensional vectors, when you multiply them with each other, that you do row times column, where you take each value in the row and multiply it with each corresponding value in the column. So A1 times B1 plus A2 times B2 all the way through. And that gets you the right result. While that is a very good rule and it works nicely with small matrices, there are certain things that don't naturally come out of this way of thinking about multiplications. And so I think there's a different way of looking at it. And that one will scale up towards matrix multiplication nicely. So the way that I like to think about it is that we have here a list of numbers, A1 through AN, and here we have a column of weights. And this column of weights tells us how much each number inside of this list here will contribute to the final result, which again is just a single number, right? Here's the sum of products. So this will be some number that might be, what's almost likely guess, 42, potentially. How do you get that number? Well, that number here is a weighted sum of all of the terms that are inside of, or all of the numbers that are inside of this row vector, this bra A here. And so how do you know how many A1s will be in 42? Well, B1 tells you how much of A1 will be in 42. So you're going to get B1 times A1. That is the amount of A1 you're going to find in B2. And then you add to it however much A2 you're going to get. And A2 is going to be weighted by B2 times A2. And you continue that until you have Bn times An. And what you might see is that here is the same as this. You can multiplication is commutative, so you can turn it around. So these are exactly the same. And yeah, so you can do row times column, and that might be very familiar because you've done it before and it gets you this equation. Or you start thinking about, oh no, this here is actually a weighted sum, and these are my weights, and these are the terms that are being weighted. I think that second way of thinking will get a bit further, but we'll go more into it later. Okay, so what do we call this A-B thing here? We call this a bracket product or inner product or dot product. So many names for the same thing. Let's call it bracket products for this course because we're using this bracket notation. Okay, so if we have a vector A, we can write it as a column vector. So this is a ket, or we can do something to it which is called transposing it. That means we take all of the numbers that were firstly in a row and in a column, and we write them in a row. So we form this bra vector that has the same numbers in it, just in a row instead of a column. And now the question is, what is going to be the bracket product of the same vector? Like if you have the same vector, A, then you transpose it to get transpose the ket vector to get the bra vector, and you calculate the bracket product. What will it be? Particularly, what will be the bracket product of a unit vector? We already encountered a unit vector before. We had this guy here. Yeah. So one thing that we recall is a vector is only a unit vector if the bracket product is going to be 1. Why is that? Well, we're going to find that. We find that now. Do we find it or do we assume it? Let's think about this. Are we just saying that here? We want to show it. Let's think about it for a second. Let's just do the exercise. So what's the bracket product of this unit vector here? So we're first going to turn this ket into a unit vector. So we're going to do transposing. So we turn it into 3 over square root of 10 and 1 over square root of 10. And then we multiply it by its ket, 3 square root of 10, 1 square root of 10. And now we remember these are the weights that each of these numbers will have in order to calculate the final bracket product, the final dot product, the final number. So we have 3 square root of 10, 3 square root of 10s. So that's just going to be 9 over 10. And we have 1 square root of 10, 1 square root of 10s. Oh, 3 times 3 is 9. 1 times 1 is 1 over 10. No square root. Because square root of 10 times square root of 10 is 10. And then we have 10 over 10, which is 1. And that's in general true. If you have a unit vector and calculate the bracket product, that's effectively the same thing as using the Pythagorean theorem. You say square root of this plus square root of that. And if the result is 1, then you have an orthogonal vector or not. Well, that's what we're trying to prove here. There's an exercise for you to repeat in your study journal. We're supposed to prove that if you have two vectors A and B, that they are only orthogonal if the product between the bracket product between A and B is equal to 0. How would you go about that? Well, let's grab two-dimensional vectors, a ket 1, 2, and another ket 1, 2, this B1, B2, and then let's calculate the sum over both. A plus B is this. So what do? We have effectively two vectors, a vector A that might point here, a vector B that might point here. And now we just calculated that there is this other vector A plus B. Right, and we can say that they're all column vectors. Great. Now, if we use the Pythagorean theorem, or ask ourselves, what is the length of this vector here, a squared plus b squared, then we have seen before that we can calculate the length of this vector either by using the Pythagorean theorem, a squared plus b squared, or we calculate simply its bra-ket product. So we take the AB vector and write it once as a bra and once as a ket, so we can multiply them with each other. Or we write it out, which ends up being the same thing as let's do it here. So we have A1, B1 plus A2, B2. So that is the contribution, the weight times this plus this weight times that guy, brings us to this line. And then from here, we simply square the bracket away. So we get A1 square plus 2AB, A1, B1 plus B1 square. Do the same thing for the second bracket. That gets us to this line. No magic happened yet. Now we just rearrange terms a bit. We have here A1 square and here A2 square. You don't need these parentheses when you have a sum. There's no reason to write these out, so you can just drop them and then rearrange the terms. We rearrange them so the square terms are here for A1 and B1, for A1 and A2. The B1 and B2 terms are here, and then everything else is being collected here. Now, if you look at that, you see that A1 square plus B2 square is just A to the square, like the length of the A vector. B1 square plus B2 square is just the length of this vector here. And then the rest that you have here is 2 times the bra-ket product between A and B. All right. So now when is this guy equals to this guy down here? Oops, let's clean up house. Okay. This guy is only going to be equal to what's down here. Well, this is always equal to that. We just showed that generally. However, when are A and B orthogonal to each other? When do we have this situation that drew up before, that we have an A and a B, and they have a 90-degree angle between them? It's not working well. A and B. When are they at 90 degrees? Well, we saw before that the Pythagorean theorem would say that when these guys are 90 degrees, then they form a triangle where the long length here is A plus B. And if the Pythagorean theorem holds, then A square plus B square, wow, the pen is not working, is equal to A plus B square. So this side square plus this side square is equal to the hypotenuse square. If you compare it to these terms here, we have the A plus B square, the right side, up here, and we have the A square right here and the B square right there. So for these to be equal, we would need to assume that this guy here is nothing. we would somehow need to assume that 2 times the bracket product of A and B is 0. And that's actually the general rule here. It's shown in 2-dimensional, but you can maybe you want to do it in your journal. Show this for n dimensions as well. So 2 vectors A and B are orthogonal if their bracket product is 0. That's an important thing. So we want to remember that. If you want to check if 2 vectors are perpendicular to each other, orthogonal to each other, you just calculate their bracket product. If it's 0, that's it. With the dot product interpretation, it makes a lot of sense because you have one vector here and one vector here, and you ask yourself, what is the projection of this guy on that one? What is the size of the shadow this vector would cast on this vector if it has an angle to it like this? You would shine a flashlight from up here on this vector. You would see that there might be this shadow cast on it. But if this vector points straight up with a 90-degree angle and you show a flashlight on it, this vector is not going to cast a shadow on this. So the dot product is 0. The bracket product is 0 when you have orthogonality, when 90-degree angle between them, it's then 0. So different ways of looking at the same statement. Okay, great. Now we should understand what orthogonal vectors are, and we understand what unit vectors are. Now we're going to combine the idea that there are certain vectors that are length 1, they're unit, and they are orthogonal to other vectors. Now, if you find a combination of vectors that are all unit vectors and they're orthogonal to each other, they can form something that's called a basis. Now, a basis is the smallest number of vectors that you need to open up a vector space. Opening up a vector space means in our 2-dimensional case, those are 2 vectors that if you combine them with each other, they allow you to reach every point in that 2-dimensional space. Lots of vectors can be used to reach everything in the space as long as they are linear independent. But we particularly care now for the smallest number of vectors. So in a 2-dimensional space, that would be 2 vectors that are both length 1 and they have a 90-degree angle to them. So yeah, we can discuss in class what it actually is that makes what these 2 vectors have to have in common. Simple example for 2 vectors that would do that are the 1 and the 0 vector. So if you think about the coordinate system, see if my pen wants to work now. If you have a coordinate system and you want to reach any point in this 2-dimensional space, let's say this point here, you can ask yourself, how do I get there? And you can say, well, I take a defined number of steps in the x direction. That would be this first vector here. Those are steps in the x direction, 1 in the x, none in the y. And then a certain number of steps in the y direction. This is this vector here. And then I would get there. And so maybe I need 4 times this vector and 5 times this vector in order to get there. And similarly, I could get to this point or to this point by maybe taking a negative number of steps in this direction and up, or a negative number in this direction, positive number in this direction, a negative number in this direction. Okay, so the cool thing about these 2 vectors is if they are what they claim to be, which is unit vectors and orthogonal, then their bracket product with themselves needs to be 1, because unit vectors, bracket product is 1, both of them. And the bracket product between them has to be 0. That just says they're 90 degrees on each other. Cool. So what's now a basis? A basis is a number of these vectors that corresponds to the number of dimensions that you have. So 2-dimensional space needs 2 of these vectors. It's an orthonormal basis if both of these vectors are 90 degrees on each other and they have each a length of 1. So something that you can check in your study journal is that these 2 here are these big Wirvly brackets, they mean those are sets, that these sets make up orthonormal bases. So how would you check it? Well, you would have to check that this vector has a length of 1, that this vector has a length of 1, and that the product of both of these vectors is equal to 0. And the same here. All right. Maybe we are now at this point that things will start to make sense that we said at the beginning of the course, of this lecture. Let's look at this one slide, this one image here, where we have all of these arrows. These arrows are representing different vectors that can form an orthonormal basis. So the up vector, maybe the spin up vector, if you want to call it like that, that's the one that goes 1, 0. Now you might say, but we always said this is the x direction. That should be a vector that points to the right. Yeah, there's a bit of discrepancy in how you want to call things and how you want to label them. But we just remember a 1, 0 is a vector that points straight up. Actually, the book has some questionable decisions at times in which direction it draws these angled vectors. You can actually find errata on the book on this website here. But for us, let's just stick with this and it will be fine. So let's just remember pointing up is the vector 1, 0. Pointing down is the vector 0, 1. Pointing to the right, that looks a bit more messy. But what does this actually mean here? It is one step up and a step to the left. What would that look like if we would draw that in two-dimensional space? So this one here is going up. If we say this is up, it goes up and it goes to the left because of the minus sign. So we're going to go up and left, and then we're going to get here somewhere. So that would be a vector that points somewhere like there. But we have to make sure that this vector is a unit vector. And what's the easiest thing to do? Well, if this is the length of 1 and this is the length of 1, then the length of this guy here is the square root of 2. So that's going to be too big. So what we have to do is we have to take we have to divide it by the square root of 2 in order to make sure that this is a unit vector. So that's where the square root of 2 comes from. It's a normalization factor to make sure that this here is a useful vector pointing here. Now, if you point here, what are two vectors that would be orthogonal to it to allow us to form a orthonormal basis? Well, one of them could be a vector that points here, and one of them could be a vector that points here. Those both would form 90-degree vectors to it. If we look at this guy here, that's the partner with it, that's a step to the right and a step up. So this would be this vector. So, here's the 90 degrees, and you can see that this would be sort of a 45-degree rotation of the normal coordinate system that is spanned by the 1, 0 and 0, 1 vectors we may be more familiar with. And then finally, here's this guy. That looks a little bit harder. You have a 1.5 and then this weird square root of 3 thing. It's like taking a little step up and then a little step to the left and then somehow stepping up and stepping to the right. So it's somewhere similar, but not quite the same. Now, why do we need this weird combination? It turns out to be a useful one later on. Can't really motivate it very well with what we know so far. So let's just say that those are two vectors, and you can convince yourself that they're length 1 and that their bracket product is equal to 0. So they form orthonormal bases. Now, instead of writing all these numbers, we just write them down as arrows, which nice shorthand. If you have no idea how the arrows are defined, this makes no sense. But now we know that these arrows just correspond to column vectors, cats, or to on the left side to transposed column vectors or bras. Okay, now if two vectors point in the same direction, two arrows point in the same direction, that means, well, it's the unit vector bracket producted with itself. So by definition, since the unit vector, these things, when they're the same symbol, they always must be 1. All right, so these first 6 numbers should be super clear because the same vector is effectively just calculating the bracket product of a unit vector. So that's 1. And what's up with these guys here? Well, here we have the combination of the two orthogonal basis vectors. So they are orthogonal to each other, so their bracket product is equal to 0. So whenever you have the two matrices opposing each other, it's 0. Now you might ask yourself, oh, what happens if I take a vector 1, like the vector up, and do the bracket product with the one that points to the side, like that? Well, that's not going to be 1 or 0, because those are not bases of they're not elements of the same bases. So don't worry about that right now. But this stuff should be super clear. Great. All right. So in general, whenever we encounter a vector, we can assume it is a linear combination of its basic vectors. That means any vector CD, which is just a point in two-dimensional space, can be reached by taking a certain number of steps x1 in the first basis direction, and then a certain number of steps x2 in the second basis direction, base vector direction. Now, obviously, if you can reach any point C and D, you might ask yourself, well, is there a formula that I can use to figure out how many steps do I need to take in x1 in the first direction and the second direction? What are x1 and x2 to get to any C and D? And that's what we want to try to find out. All right. No. Okay. So how can we solve this quickly? So let's take a concrete example. We're going to go to a point C and D, and we're going to use these right and left vectors, wherever they were pointing, whatever. So there are two vectors that form an orthonormal basis. And so we want to see how many steps do we have to take in each of these directions to get to the point C and D. Here's the math, the trick that we can pull. We can just take this expression and multiply it on both sides with the vector pointing to the right as a bra. Linear algebra tells us when I have an equation and I multiply the left side with the same as the right side, the equal sign is still true. Okay, so you notice here that we just wrote this guy in front of the left side and this guy here in front of the right side. Now, when we do the multiplication, what do we end up getting? In the first step, we are going to simplify and move the arrow into this parenthesis that we have. So we just get rid of the parenthesis by multiplying that right pointing arrow with the first term and the second term, similar to how you do multiplications with normal numbers as well. And you realize that this x1 here is just a scalar. Right? It's just a number. And you can either calculate the stretched or compressed length of this vector and then multiply it with the other vector, or you can first multiply the vectors and then stretch or compress the final result. There's again the commutative law of the multiplication at hand here. Right? So we just write the scalar on the left side. But now if we look at this, we realize that we have here two vectors pointing to the right side. So that's the bracket product of the same normal unit vector with itself. So that guy here will just be a 1. And this guy here, pointing to the right and pointing to the left, that will be a 0 because the two are 90 degrees on each other. So this whole thing simplifies to give you just x1. So you can find the number x1 simply by multiplying the raw version of this cat here on both sides. Nice. Now, if we remember what the definition of the right vector was, this was this 1 over square root of 2 minus 1 over square root of 2, we can also just multiply this out and see what happens. If we plug in this definition for the right pointing arrow, and then we do again our weighted sum. So C times the first term plus B times the second term right here, multiply it out, then we find that. So x1 is equal to C1 minus D over square root of 2. Very nice. You can actually do the same thing for x2 as well. You would just multiply with the bra of the left pointing vector, and you can find it. You should do that in your study journal. If you do that, then you can find this closed expression for CD that says, well, if you want to get to the CD point, you just go this number of steps to the right and this number of steps to the left. And the step size is completely defined by C and D. So that's quite neat. We can generalize this into higher dimensions. So if we ever do, we don't need to do it in this course, but if we ever wanted to go into n dimensions, we can reach any point in n dimensions by building linear combinations of all of the n basis vectors in this orthonormal set. And that means we can reach any point if we simply go x1 steps in the b1 direction, x2 in the b2, and so on. Now, one thing that we learned is that if the b vectors form an orthonormal basis, then every time you multiply the bracket, calculate the bracket product between a vector with itself, you get a 1. And every time you get you calculate the bracket product between like a b1 and a b4, so where the indices are not the same, you get a 0. You can write that quickly like that. So the bracket product between two vectors is always going to be 0 if the two indices are not the same. Otherwise, it's going to be 1. And then we use that trick. That's when we want to figure out how big x1 is. We multiply the bra vector for b1 on the left side. Then everything here on the right side gets to 0. And I'm only left with the bra b1 vector times v is equal to x1. And since I can do that for every term, I can just go in and replace the different x1s here with the bracket product of the corresponding basis vector with the final result, that point that you want to reach. Okay, great. So this thing here actually has a name. This here is how much of B1 will be in V. We call it the probability amplitude. It's not a probability. It's an amplitude for how likely we're going to find some part of B1 within V. All right, great. So that's a word you want to remember. We're going to come back to it. Probability amplitudes will be very important. Great. So here, reading quiz. If you read the book, you should notice that this on the left side is not the same as that on the right side. On the left side, we're having a set. And a definition of a set is it is an unordered bag of things. So it's really just a bag you stack things in, and you can shake it and grab something out randomly. So no one tells you in which order things are in a set. When you have these round parentheses, then you have what's called an ordered set or an ordered list. And so this here is a basis set, and this is what we call an ordered basis set. So here you cannot randomly pick something. Things are coming in predicted order. And so this effectively says if it's two elements in here, if you use these round parentheses, you can rotate them around, shuffle them around randomly. It's always the same. An ordered basis set is not the same if you first point up and then down, or first down and then up. Not the same. So it's sort of a question, does order matter? And for experiments, you might recall it really matters. If you, for example, have a magnet that has the south pole on the top and the north pole at the bottom, that might correspond to the up one. And then the down one might correspond to the south pointing, south on the bottom and the north pointing up. And these two magnets, they will impact your electrons or your ions that fly through there differently. And so it clearly matters if you are going to measure first this way or that way. And so ordered basis set, they're pretty important. They will help us define in which way we actually measure stuff. So be aware of that difference. Okay, finally, length of vectors. If we now accept the fact that given an orthonormal basis set, B1 through Bn, and a vector V in this n dimensions that can be rewritten as this linear combination with probability amplitudes for each basis vector calculated by the bracket product of that basis bra multiplied by the final vector V, then we can simplify our life a bit and just rewrite these probability amplitudes as C1, C2, all the way through Cn. Right? These are the probability amplitudes. And then we use the Pythagorean theorem in high dimensions, which happens to be the same as in 2 dimensions. In 2 dimensions, you have a squared plus b squared equals c squared. In n dimensions, you have a squared plus b squared plus c squared plus blah, 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 blah until n squared. So the length of this vector here is going to be the bracket product of the vector with itself. And the bracket product, what is the bracket product of this thing by itself? Well, remember, if you have here this really long ket vector, you write it out as a bra vector again, and you multiply the two by each other. What did we see before? So if I take this guy here and write it as a, I guess you're supposed to do it yourself. Are you? Yeah, you're supposed to prove this yourself. So I won't prove it for you, but it's quite easy to see that if you take the so these are ket vectors. If you take the bra vectors for them and multiply them with it, calculating this guy here, then you will get a 1 for wherever the bracket of the same basis with itself is calculated and 0 everywhere else. And so you end up just with the indices of the probability amplitudes to the square left over. So there's a C1 square that's multiplied by 1. All the other ones, the C1, C2, C1, C3, there we all multiplied by 0 and drop out. And so after some simplification, you will find that the length of the vector is simply the sum over the squares. And then the full Pythagorean theorem, of course, you just take the square root on both sides, and then you have the length of the vector is the square root of the sums of the squares. Okay, great. So now if you have a collection of bras or cats, so if you have, for example, 2 row vectors, then you can write them into a matrix. And so this is a matrix. This is effectively a collection of rows. You might also see it as a collection of columns. There's a 1, 2 column, -4, 3 column, and a 2, 0 column. So who tells you that this is a row and this is a list of 2 row vectors and this is a list of 2 column vectors? No one can prescribe the way you look at the math. But what is pretty important so there's one important operation that you need to be familiar with, which is called transposition. We've seen it before. It is when you take a row and write it as a column, or a column and write it as a row. And here we have, for example, the transposes of these A and B matrices given, where the AT is the transpose of A, which means we take the first row and write it in the first column, or take the second row and write it in the second column. Similar for B, we take the first column and write it in the first row, or the second column and write it in the second row. And then depending on how you look at it, you might also say, well, actually, I took the 1, 2 row and wrote it in the 1, 2 column, and the 7, 5 row and a 7, 5 column. It's interchangeable how you think about it. But the idea is just that you take the rows and make them columns, or you take the columns and make them rows. Just pick what you like to do and do it always. And that way you don't mess things up. Okay, great. Now that we are able to do these transpositions and whatnot, we might want to think for a moment about how to do matrix multiplications. So if I have 2 sets of rows and a set of 2 rows and a set of 2 columns, and want to multiply them with each other, how do I do that? How do I calculate A times B? Here's a way given, so they write the A, they say this is a row vector. So you write it as a bra. The 230, you write it as a bra. And then the 173 is a cat. You write it as B1. The 251, you write as a cat. And then if you do the multiplication, you have, they're doing here row times column. That gets you A1, B1, row times column A1, B2, row times column A2, B1, and row times column A2, B2. Okay, and then you just take all the numbers in A1 and multiply them with all the numbers in B2. So it's this big old rows times columns thing, which I'm not so fond of. I really like a different way of matrix multiplication better. And so what I would do instead is I would write out the A matrix and interpret it as 4 column vectors. Wow, this is just ugly. So this is supposed to be a 2, supposed to be a 3. These pencils not working well. This 2. Okay, so this is the A matrix, and then you multiply it by the B matrix. So the 1, 7, 6, 2, 5, 1. And now the way I would interpret this is these are 3 columns. There's a 1, 2 column, a -4, 3 column, and a 2, 0 column. And each of the columns in the B vector give us the weights of how much each of these columns will be represented in the final matrix. So I would have 1 times this column, 7 times this column, and 6 times this column. So that would be 1 times 1 plus -4 times 7, 28, -27 plus 2 times 6, 12. That would be -15. And then do the same for down here. So 1 times 2 is 2. 3 times 7 is 21. So it gives me a 23. And then I would see that here the -15 and 23 are the same as the numbers that I got down here. But the way I thought about it is that this first column vector in my results is a linear combination of the column vectors in my A matrix, where the first column in the B matrix gives me the weight of how much each of these columns contributes to this final column. And you can do the same thing also for the second number of weights, and then you're going to get -16 and 19. Okay. Why do I like this better? I like it better because it gives me a way to think about the dimensions of the problem. So we're going to see that on a next slide. So if we have this multiplication A times B, we sometimes want to think about, well, what do we receive at the end? We have a vector A that has m rows, right? These are all rows here. A1 is a row, A2 is a row, AM is a row. So we have m rows. How many columns are in each of the rows? We don't know that, right? We don't know that. Yeah, we just know that there are m rows. The matrix B here has columns. How many columns? We don't really know. We know it's n columns, but how many rows in each column? It doesn't say it, right? We don't know. We know that M has a certain number of rows. That is M. A has M rows. Gosh, what is not right? M rows, and then some number of columns. We don't know what it is. Let's call it what? P. P rows. How about B? B is going to have some number of rows, which we don't know, and a certain number of columns, which is n, is given here. So there's definitely n columns. But how many rows does it need to have? Well, if you think about it, each of these columns here, this B1, needs to contain weights for each of the columns in the A matrix, right? The A matrix has all of these columns, and this B1 here tells us how much each of these columns is going to contribute to the final result. And since there are P columns in A, there must be P weights, P rows in each of these column vectors. So we have P times M. Great. And now so this is N. So if you now calculate the product, what are you going to get? Well, each of these B's here is going to give you a set of weights that you use to combine the columns in A. Correct? Yes. All right. So how many times are you going to combine the columns in A? Once for each B. So there's going to be n times that you're going to do it. So you're going to end up with n columns in your result. And then how big is each of these resulting vectors that comes out? Well, they're going to be linear combinations, additions of these m deep. So it's a column vector with m rows plus a column vector of m rows plus a column vector of m rows. So you're going to get out these m row long vectors. And so you're going to get an m cross n number of, so m rows and n columns in this product A times B. If you want to look at what this looks like, it will look like that. You're going to have the bracket product in each of these elements. There's going to be m rows and there's going to be n columns. Yeah, so you can also just remember it that you have an m cross p times a p cross n matrix, then the result will be an n cross n. But if you wanted to think about it, I feel this linear combination of column vector idea, where the second matrix gives you the weights with how much they all add up together, lends itself to a more intuitive interpretation of it. Great. Now there are some special types of matrices. Those are the ones that don't change stuff. The simplest one is 1. The 1 by 1 matrix has a single number in it. If you multiply something by 1, it stays 1. There are other matrices that have the same property. If you multiply a matrix A with that specific matrix called I, identity matrix, then it is not going to change your matrix A. So I times A is the same as A times I. It is always the same as just saying A. Multiplication by 1 with matrices. Now, which dimensions does your identity matrix have to have? Well, think about it. Again, if you write it on the right side of your matrix A, it needs to give you a linear combination that takes 1 time the first column in A, 2 times the second column in A, 3 times the third column in A, and then depending on how many columns you have to have in A, you will have to add additional elements to this identity matrix here. So if A is a matrix with let's say 5 rows and 3 columns, then your identity matrix needs to be able to take each of these columns and multiply it once by 1, so that you grab each column once and then you spit out the initially inputted matrix A again after the calculation. So you want to have the same dimensions as the largest dimension of A, and then you just make it square. So the same number of rows and columns with ones on the diagonal. That's the easiest way to do it. Okay, great. So does matrix multiplication make your life easier or harder? I hope this slide will show, it makes it easier. So if you want to check if this, is it ordered or unordered? This is an unordered set. Okay. This unordered set is an orthonormal basis or not. You want to find out if each of these elements in here multiplied by itself, so the bracket product of itself will be 1, and the bracket product of itself with of any vector with any other vector is equal to 0. So the fast way of doing that is we're just taking all of these column vectors, write them out, and then we transpose it to create a matrix of the bras of the row vectors, and then we calculate the product between the bra and the cat matrices, and that is going to give us this expression here. And so if you look at these numbers, what do you find here? You have the elements of the orthonormal basis multiplied by themselves as bracket products along the diagonal, and you have the mixed terms everywhere else. If it is an orthonormal basis, then only the elements on the diagonal are allowed to be 1. Everything else has to be 0. And so all of these terms here should be 1, and all of these terms should be 0. That means this here should give you a square matrix with only ones on the diagonal, which would be the, given that this is n by n, the nth identity matrix. So that's a very quick way of checking if you have an orthonormal basis. You just take all of these vectors and calculate the bracket product with its transpose. And if that's unity, the identity matrix, then you're done. Then you've shown that that's an orthonormal basis. And since these multiplications super easy to put into a computer, you don't have to do this by hand. You just let the computer do it and then check, do you get the identity matrix or not? It's a very quick way of checking for an orthonormal basis. Great. Now, if we know that we have an orthonormal basis, we should be able to express any vector v as a linear combination of these orthonormal vectors. And we can do that by calculating these probability amplitudes we've seen before. Now, if we think about this in our new appreciation of weighted column vectors, maybe we notice something. If you think about this here, on the right side, you have these column vectors, b1 through bn, and they're all weighted by these probability amplitudes. So you could rewrite this line by saying, hey, I just write out all of my column vectors, b1 through bn, and then these probability amplitudes I write down as the weights by which they're being added together, like that. Now, if we call, so what is A? A is just a matrix of vectors that form an orthonormal basis. And since they form an orthonormal basis, we know that A times its transpose is going to give us an identity matrix. So if we take the transpose of A and multiply it on the left side, in this equation here on both sides of the equation sign, then it's this new superpower that we have, multiplying by the transpose of A on the left side gives us just the transpose of A times V, which is the same as writing out the former cat vectors as bra vectors. And on the right side, we have A times its A transpose times A. And this is just the identity matrix. So this guy is just going to be gone on the right side, and then we just have the probability amplitudes left on the right. And so if we want to figure out what CD is, we can very simply use this trick here to simply write out the right and the left vector by taking their transposes. So instead of writing this as a cat, we write it as a bra, and this one we write as a bra, write it on the left side, and then you instantly get out what x1 and x2 are. So that's really neat. So we can very quickly find the probability amplitudes of this expression here by simply taking the orthonormal basis and multiplying it by V. All right, great. So yeah, there are a couple of matrices that are pretty important. This one here is the so-called Hadamard gate. This one is the C-naught gate. We're going to talk more about what gates are later, but I'm just showing them to you now because they're kind of important. They're cool because they are orthogonal matrices, which means that they also have this property that if you multiply them by their transpose, you're gonna get the identity matrix, and that will be quite useful later on. Yeah, we want to build algorithms, and those will be the gates we use for it. Very nice. So these matrices are called orthogonal for us because we're just looking at the real part of complex numbers. If you actually use the whole complex numbers with imaginary part, you would call these unitary matrices. But let's not worry about it, just so you have heard the word once. Okay, now the question is, we spent almost 80 minutes on this lecture. Was it worth the effort? I believe it was, because what we have seen now is that if you are being handed this bag full of vectors, these ket vectors, you can see if they form an orthonormal basis or not, simply by taking this matrix of ket vectors, calculate the transpose of it by writing them all as bra vectors. Oh, no, it's actually bra. Write them as bras. Then take this transpose, the bra vector matrix, times the ket vector matrix. And if you get an identity matrix to come out, you are able to check that we have an orthonormal basis. Very cool. Along the same lines, you can now express any vector v. You can find it as a linear combination of these basis vectors by simply calculating the transpose of your basis vectors and multiplying it by that ket that you want to represent. And you instantly get the probability amplitudes that allow you to form the linear combination to get to that vector v. Very nice. And then finally, since you have now a nice way of getting these probability amplitudes, you can very quickly go about finding the length of any vector v simply by calculating the square of these probability amplitudes and then take the square root out of it. So those are your new superpowers. This is honestly the math that you need for 90% of the course. There's a couple other topics like tensor products we're going to go into, but there won't be like such an overload of math concepts at once again. I have this also as the second lecture because of the add and drop deadline of the course. So if after this you say, this is kind of interesting, I think I can do it, then I'm sure you can do it. But if you say, oh my goodness, let me out of here, then this is the moment to just quit the class and leave it. And I won't be offended because although the book says quantum computing for everyone, I'm pretty sure that some people in my close proximity would not be willing to put the effort in to fully understand this. But if you lasted up to now, I'm pretty confident that you'll be able to make it through the rest of the course. And again, we're going to review this as we need it. And you should have everything to be successful if you can understand this slide here. Okay, with that being said, see you next time. Goodbye.